Hello, and welcome to another lecture. So we're moving on to chapter 2, looking at subsection 211. And so we're finally going to get to what holomorphic functions are, at least get to the definition today, or in this lecture. So let's consider a polynomial. These are really nice functions. It would be great if we could just work with these sort of functions, right? Basically just a finite sum of powers of z, right? So polynomial in a complex variable. So these are great. These are lots of things that you can do with them. But unfortunately, there's lots of things that you can't do with them. They're easy to work with. A lot of times you just use algebra. But yeah, there's some things that you can't do because there just isn't that many of them. I mean, in some sense there's a lot of them, but in some other sense there aren't that many. For example, if you want to solve some differential equation, like the derivative of f is equal to f, yeah, that's not something that you can solve as a polynomial, except for 0. Right, 0 is a polynomial that solves that, but there's no other solution, no interesting solution. So let's look at some one property of polynomials that that we can generalize, that we can try to figure out. Well, let's look at other functions with that property and study those. That's essentially what we're going to do in this entire course. So let's expand P around some fixed point z0, right? Well, I mean, just a little bit of algebra, right? I can just write it as a polynomial in the difference between z and z0, right? Now that's the same thing as writing the difference as h, right? Some complex number h, and writing as a polynomial in h, right? And so I have these c0 through cn are the coefficients. So it's just some fixed complex numbers. All right. So now let's compute basically what looks like a derivative, right? It's going to be the derivative. It's going to be the complex derivative. So let's look at the difference quotient of at z0, at that fixed z0, and let's try to take the limit of this difference quotient as h goes to 0, right? And it's just a little bit of algebra right now. P at z0 is just c0, right? So that's easy. And then if I take this guy and I subtract p0, I'm left with this, right? Just this thing over here. And that's clearly divisible by h, so I can cancel out an h, right? And then I get c1 plus something that depends on h, but that actually is 0 when I set h to 0, right? So that means that I just get c1, right? And basically, essentially by algebra, right? It's just canceling out, right? This is just calculus one way of computing limits. All right. Well, that means that this polynomial, thinking of it as a function of h, is locally near z0, approximated by this affine linear expression. C0 and C1 are just complex numbers, right? And so we get this nice approximation. If it was real, it would be a line. So this is, it's the graph is going to be a complex line in this case. So all of these are complex numbers, but it's this affine linear guy, right? And the error vanishes faster than h. That's really what this thing says, right? We're computing the error from between the polynomial and its linear approximation, or affine linear approximation, right? Affine means adding a constant, right? That's all that means, right? So this is supposed to be the best affine linear approximation for the function, and for polynomials we have that, right? Now, just to emphasize, all these limits, right, that we're taking, and all these limits that we're going to be taking are as a complex h goes to 0, right? So the h varies over c, not over some r or whatever. It varies over c, so there's lots of ways to approach 0, right? That's a very key point here, right? We're not taking, h is not some real number or some purely imaginary number. It's any complex number, right? So it can approach 0, in any old way, right? So that's, if you have a limit existing, that puts, that's stronger than saying just for real h, right? Much stronger. All right. So we want functions. The functions that we want to study are functions with such a derivative, right? Basically, we want functions that can be approximated by c0 plus c1h near every point, right? That's basically what we want. We want functions that have this property that came from polynomials. So really what we want is an f such that at z0, I can look at the f a little bit away, right? Plus h away. And that I can approximate by this affine linear, right? So it says that, I have this affine linear approximation. C is just some number. It's really that's going to be the derivative, right? And then this is the error, right? And that's supposed to go to 0 faster than h, right? That's what that little o of h means, right? So, well, let's just do this definition, right? So a function f is going to be complex differentiable, right? Not just differentiable, complex differentiable at z0 if this limit exists, right? Maybe a little bit of, let me emphasize it. I'm always going to use complex differentiable when I mean this thing, just to emphasize that that's the complex derivative, not the real derivative, right? In this course, if I say differentiable, it's going to mean real differentiable. I'm usually going to say real differentiable. And this is complex differentiable, right? It's complex differentiable because this h is complex, right? That's really what's the, we're going to see the relation to a real differentiability. I mean, it's a function of form R2 to R2. So the real differentiability is not as simple as difference quotient. All right, so we have it's complex differentiable if this limit exists, and we call this the complex derivative, right, of f at z0. And sometimes it's useful to use this sort of Leibniz notation, df dz, right, for this derivative, and we're gonna say f is holomorphic, and it's going to be a word that we keep using over and over, if it's complex differentiable at every point, right? So holomorphic means complex differentiable at every point, right? That's what that means. So those are the functions that we really want to study, are the holomorphic functions, right? That's basically what this course is about. It's about holomorphic functions. All right. So what did we prove above? Well, basically, in the in the introduction to this lecture, we proved that if we have a polynomial, then just by a little bit of algebra, we have that it is holomorphic, right? We actually found that we could compute this limit in a very trivial way, basically by algebra. So we have that polynomials are holomorphic functions. Good. I mean, that means that we're generalizing polynomials. That's what we wanted to do, right? So an exercise, this is not hard to do, showing that if you have a holomorphic function, then it's at least continuous, right? I mean, it's going to be a lot more than that, a lot better than that, but at least continuous. It's the same as how you would prove that a real differentiable function of one variable is continuous, right? It's basically the same proof. The idea is, I mean, this is, you have the difference quotient, right? That's the only way that it's going to exist if the numerator goes to 0, right? Which is precisely what continuity is. So it's not too hard to prove. So holomorphic functions are continuous. Definitely not vice versa. There's a lot of continuous functions which are not holomorphic. Vast majority. So, all right. So next time, what we're going to do is we're going to look at the relation of the complex derivative to the real derivative. And we're going to look at the Cauchy-Riemann equations, and that's really gives you the relationship between these two. All right. So we'll do that next time. So see you next time.